Bismillah ar-Rahman ar-Rahim. This is Steel Structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University on April 2nd, 2020. Today, inshallah, we're going to talk about torsional and flexure torsional buckling, and then we will move to build up members or sections. If the compression member is loaded axially, it will be unstable, which is overall instability or instability, not the local buckling. Overall stability means, or instability means the buckling or global buckling, or we do have a local buckling. I think I explained to you what does this mean to have a global or local buckling for the compression members. So this compression member, it will buckle or fail in three ways. The first way is under flexure buckling, and all our study for this chapter was based on flexure buckling. يعني كل درسنا كان based on flexure buckling criteria. So the deflection here for the compression member, it will caused by the bending or flexure about the axis corresponding to the one with the largest slenderness ratio. تذكروا قلنا if we do have a column, so all the time supported differently in both sides or both direction, we will take the largest slenderness ratio. When we tell largest slenderness ratio means the minimum R here, okay? The smallest radius of gyration, so for the cross section, okay? So, and any compression members with any type of cross-sectional configuration can fail in this way, which is the flexure buckling. And let me show you how that looks like. So here, guys, if we do have a column here, this is a column, okay? Loaded axially. Axially means perpendicular to the cross section here and there. So this one, it will buckle this way. So we do have bending here. So if this is the cross section, guys, it will transfer or move, which means here. يعني كأنه اتحرك الكروس section, okay? فهذا بنسميه الفلكسure buckling. And we do have two other types of buckling. Let's get back here. We do have torsional buckling. Torsion means twisting, okay? And this type of failure is caused by twisting about the longitudinal axis of the member, okay? And I'll show you in the sketch what does it mean. And this will happen only for doubly symmetrical cross sections with very cylinder members, okay? So the cruciform shapes, which I'll show you right now, it's susceptible for this kind of buckling, okay? And let me show you this in the sketch. So this is the torsional buckling. The same column loaded axially with a different cross section. The same column, let's say, in the length and but not in the cross section, because the cross section here is wide flange and here is a cruciform, which is يعني صليبي. And this kind of cross section, it's a symmetrical one, okay? Symmetrical, okay? لو عملت cut hone or axis of symmetry here and there, you will see it's a symmetrical shape in geometry. So in this way, twisting will happen. Twisting يعني means التواء. راح يصير له التواء، اوكي؟ بدون ما يتحرك من مكانه، just يعني twisting. So that's what we call it torsional buckling. The third type, which is here, which is this one, flexure torsional buckling. It's a combination of this type and this type. يعني تجميع من هذا ومن هذا. There is a flexure buckling and there is torsional buckling. So in this type, it will happen for unsymmetrical cross section. So here it's unsymmetrical. لما أحكي unsymmetrical, it might has one axis of symmetry or it's not symmetrical at all. يعني ممكن يكون في عنده one axis of symmetry فهذا أكيد symmetry in this way but or sorry this way. هذا هون بيشبه هذا it's symmetrical about this axis but it's not about this axis. Okay, so this one it will buckle flexure and torsional فهو انتقل من مكانه وبنفس الوقت صار له التواء أو twisting فهذا بنسميه الفلكسر torsional buckling. Okay, so once again this is the axis of symmetry. Okay, it's x, it's a symmetric about x-axis but is not about y-axis. So we do have one axis of symmetry. If you look at this back here we do have x and y. Okay, and the cross section is symmetrical about x and about y يعني متشابه حول ال x ومتشابه حول ال y. Okay, so that's what we have and that's what we have if we have symmetrical or unsymmetrical cross section. Okay, the other thing here, kind of this cross section, it might be a built-up section or it will be a built-up section because we don't have any hot rolled standard cross section like this. So that might be, it's a combination of angles placed back to back, or here 4 angles they are. Okay, welded or plated together, or might be just 2 plates or plates actually welded together. Okay, something like this. So in this, I just wanted to familiarize yourself or to familiarize you, sorry, with these topics or concepts. And let's move to the built-up members. Built-up members. Why we need to use built-up members? As I mentioned to you in our face-to-face classes, to increase the available capacity of the cross-section, we might need to build up a section or a member. Means all the hot-rolled standard shapes, they might not be able to carry a required load. يعني اللود المطلوب منا to be carried مع أن أي section بالستandard shapes ممكن يحمل هذا اللود. We might use the built-up section. What does it mean to have a built-up section? As I mentioned earlier to you, a built-up section might be a combination of 2 or more hot-rolled sections. يعني ممكن يكون لنا, as I just showed you, إنه 4 angles or double angles welded together. ممكن يكونوا 4 طبعا that based on our demand يعني بيعتمد على اللي احنا بدنا اياه. اوكي, فهذول صاروا built up section. ممكن يكون double angle back to back. اوكي, here and there. ممكن يكونوا, yeah, this is the first type of built up section. The second type, we might have a plates, as I just mentioned to you, 2 plates like this or more form a cruciform built-up section, or we might have a built-up girder plates welded together. This one plate, this is another plate, and this is another plate welded here and here to come up with, let's say, a deep girder. Yeah, that depends what we do have in our case. And the third type is if we do have a combination of 2, let's say, rolled shape or a rolled shape with a plates. يعني if we do have a wide flange shape, this is a standard shape. يعني okay, you can get it from the manual means. We do have all the geometrical and properties for this cross section, and we might have what we call it a cover plate here, and the purpose is the same, to increase the capacity of the cross section. So this is a cover plate welded or bolted to the and mainly is welded to the upper flange, and we might have it to the lower flange, and same here for the whip. Okay, so these are the three ways how to build up members. Okay, let's take an example and see how we can calculate the compressive strength for a compression member or built up compression member. So in example 4.17, we do have the column shown in figure 4.19, which is this one. It's a wide flange 18 by 65, and it's there is a cover plate welded to the upper flange, which is 3/8 by 4, and 3/8 is the thickness and 4 is the width. So it's fabricated by a welding 3/8 inch by 4 inch cover plate to the flange of wide flange 18 by 65, okay, which is this one, guys. So this is the cover plate, and 3/8 by 4 inch. 3/8 is the thickness, 4 inch again is the width, okay? And this one is wide flange 18 by 65. A steel with Fy is equal 50 KSI is used for both components. Both components means wide flange with a plate. The width length is 15 feet with respect to both axes. Yani KL is equal 15 for both axes, yani in X and in Y, okay? Assume that the components are connected in such a way that the member is fully effective, and compute the strength based on flexure buckling. And هون we will assume it's fully effective. وراح نحسب السترينث based on the flexure buckling يعني as we used to do نفس ما كنا نعمل دائما. Okay, we will neglect let's say the flexure torsional buckling, because as we mentioned, this type of buckling is for unsymmetrical, and this shape is slightly unsymmetrical right now. Why? Because we do have a cover plate welded to the top or upper flange. لما هون without the plate it's a symmetrical. The wide flange, it's a symmetrical one. But with the plate, it's going to be unsymmetrical. So the neutral axis will go up a little bit. But here we will not solve based on the flexure torsional buckling. We will just use the flexure buckling, the same procedure we used to have. Okay? Now, to do the same procedure, we need to know R. All the time we are using KL over R, so we need to know R. And how to know R? We need to know the moment of inertia. How to know the moment of inertia? We need to know the neutral axis. So we need to do all these calcs before we use or get the compressive strength for the structural member. So right now, what is the main difference between the built-up section and the hot rolled sections, the standard sections اللي هم موجودين بالستيل manual? That in the steel manual you can get all the dimension and the properties for the cross section, but here you have to get them by yourself. The moment of inertia or neutral axis, you have to do this calcs. Okay, so in the first case, let's get the centroid of this cross section. For sure it's not going to be this one. Okay, this neutral axis is just for the wide flange without the plate. So as you know, guys, and we will get the neutral axis, and we will here assume this is as a datum. Just a minute, let me clean this up. Okay, we will assume this as a datum here. Okay. This is the datum. So right now, we need to calculate. It's going to be a little bit up. We will need to calculate y, which is the centroid. It's going to be somewhere here because we have added material here, so the neutral axis will shift it up towards this material addition, okay, or addition material. So in this case, the neutral axis is equal summation of y times a dividing by summation of a. Now, we do have a plate. Let me use a different color. We do have a plate here. And we do have a wide flange here. Okay. So if we tabulate that in a table form here, guys, so the plate, the area of the plate is this much, which is 3/8 times 4. واللي هي 4 times 3/8, which is this much, 1.5 inch square. This is inch square. And y, which is the centroid of this shape. So the datum is the top of the plate. The centroid of this is going to be the thickness dividing by 2, which is here is 3/8 dividing by 2. So it's going to be 0.1875. So AY, which is this A times A times Y, فبيطلع لنا هاي القيمة, okay? And this is going to be inch cube, and this is inch. Okay. Similarly, if we do that for the wide flange, the area of the wide flange we can get it from the manual. So go to the manual, part 1, wide flange 18 by 65, you will get the area 19.10, and the y here is equal here. This one, guys, just very pay attention to this. This one is from here, from the datum here, okay, the reference point. So this distance, let me pick a different color. This distance here, from here to here to here, it's d, okay. So to here, to this point, it's going to be d over 2, okay. But we need this distance plus this distance, okay, which is the thickness of the cover plate. So this one here, it's going to be 18.4 dividing by 2. 18.4 is the depth of this cross section. If you go to the manual, you will get it 18.4 dividing by 2 to come up with this distance, which is this distance, which is d over 2, plus 3/8, which is the thickness of the plate. طبعا هون it's up to you. You might pick up the datum here or wherever you want, but you have to work like corresponding to that. يعني لازم تحل بناء على هذا الكلام or based on this assumption. So this one is 9.575. And here is the multiplication. This times this, you will get this value. Do summation right now. So this one is 183.2 dividing by 20.6, which is here, guys. So this one is 183.2 dividing by 20.6, and this one is going to be 893 inch. And it does make sense. Okay. So right now, okay, we need to calculate the moment of inertia for this cross section. Okay. Okay, to calculate the moment of inertia of this cross section, we need to use parallel axis theorem. Parallel axis theorem like this, guys, which is I, let's say x is equal I plus a plus d squared. On This is the moment of inertia about the neutral axis. We just calculated. This is the moment of inertia of the area about its centroid or neutral axis. And this is the area of the cross section, and this is D is the distance between the centroid of the shape to the centroid of the, or let's say the part or the member to the centroid of the whole shape. يعني هون يا شباب هاي اللي هي المومنت اوف انيرشيا about the neutral axis for the whole shape لكل الشكل. This one is the moment of inertia about the centroid of the part. I'll show you right now what does it mean. And this is the area of the part, and this is the distance between each or both centroids. Let's go back to the shape and show you what does it mean. Okay, here guys. So the centroid was somewhere here. Okay, was somewhere here. It's calculated from here. So this is y prime, and this was 8 point something, it's 893 inch. Okay, so in this case, to calculate the moment of inertia about this axis, okay, which is this axis, let's call it xx prime, we need to calculate the moment of inertia of the plate about its centroid, and then move it here. So this is the D, this is the area, and the centroid of the rectangular, it's BH cubed dividing by 12 plus the area, which is 3/8 times 4 times D square. Okay, for the wide flange, same. We can get the moment of inertia directly from the table, which is the manual, and then we will use parallel axis theorem to move it from here about its axis to the neutral axis for the whole shape. So this is going to be the D when we do for the wide flange. Okay, so this is the plate here, and this is the wide flange. Let's do that in a table form because it's going to be more organized. Let's just move down. Okay. Here, guys. So right now we do have a plate. This is the area, which is 3/8 times 4. This is the Y, which is the half of the thickness. And this is AY. Well, here we do have I. And I here, guys, because all these we did it early when we did calculate the neutral axis. I here for the plate is equal B H cubed dividing by 12. And this one is B is 4, H is 3/8. This is a 3/8, okay? Cube dividing by 12, which is going to be this much. 1 inch to power 4. Okay? And D is the distance between the two centroids. The centroid of the cover plate at the top and the centroid of the whole shape. And this one is going to be Y. Here, guys, it's Y prime or Y the hat minus اللي هو thickness 3/8 dividing by 2. لأن السنترويد البليت كان المنتصف من هون، اوكي؟ أو خلينا نحكي كان المنتصف لما نحكي إنه هذا الداتا اللي هو الأبر هو الداتا هون. and this is a statics. فالسنترويد لها اللي هو كان 3/8 over 2 يعني half of the thickness. الآن to move this, because we do have a wide flange, and it's so the centroid here for the whole shape, which is Y from here, Y hat or dash, is gonna be, so the distance here, it's gonna be Y dash minus this one, guys, here. Okay, so the whole is Y dash, but this area, so this, the whole Once again, this is the hole, and this is the distance, which is y hat 3/8 over 2. And this y hat or y dash, we got it 8.893 minus this much, we will get it this much, اللي هو 8.76 or 76. So that is, and here is the total, which is I, this, plus the area times the d square, and here it is. This is the result, okay? Doing that for the wide flange here. So this is the wide flange area. You can get it from the manual. I showed you how we got this, because this is the d over 2 plus the thickness of the plate here. This is a times y here, and I here you can get it from the manual for ix, okay? And here is the d, and d here is, so this is, as we mentioned, y hat, okay? It's the total here, it's y hat. And the centroid of the wide flange, بس الwide flange كان هون. This is the d here, and d here is going to be 18, it's 18.4 dividing by 2, which is d dividing by 2, plus 3/8 minus y prime. اوكي، فهي كانت من هون، هاي المسافة من هون ناقص هاي المسافة، لأنه هاي المسافة اللي هي 18.4 dividing by 2 plus 3/8 اللي هو الثيكنس، وهاي المسافة هي اللي هي إيش؟ الواي or neutral axis, y hat or y dash. So this is the difference here, which is d here. So in this case, this is d. Right now, just like I, which is this one, plus area times d square, we will get this much. So in this case, we do have, this is the moment of inertia for the shape. And this is about x-axis, okay? About y-axis, so if this is the blade, about x-axis, and this is y-axis. About x-axis, that was b here, so we told it's here when we do calculate 4 times the height here, which is 3/8 cubed dividing by 12. This is about x-axis. About y-axis, so this is going to be here. So b is going to be 3/8 times the height here is 4 cubed dividing by 12. So this is for the plate, okay? For the wide flange from the manual, you will get IY and this much. And if you look here, we did not use parallel axis theorem because this shape is symmetrical about the y-axis. فما في أي difference, okay? So the neutral axis was through the axis of symmetry. فما فيش داعي نعمل اللي هي الجزئية هاي A D square. So right now we got the geometrical properties for the built-up section. Okay, and you know, for the hot rolled sections, you didn't need to do all these calcs because they are available in the steel manual. Right now, let's get back to our normal procedure, how to get the compressive strength for the compression member. Okay, so in this case, so this is once again Ix, this is Iy, n power 4. Since Iy less than Ix, the Iy will control. And let me show you why is that. If you know, guys, as I mentioned to you, KL over R minimum. Because all the time we are taking the largest slenderness ratio, means the minimum radius of gyration. Radius of gyration is I, or moment of inertia for I, dividing by A. So the smallest I here is the Y, okay? So R minimum, it will come from IY. It will come from IY, so here KL, طبعا KL constant وR minimum اللي هي جاي من IY، فبهاي الحالة Y axis will control. Okay? Okay. So here we will get I or R minimum, which is this much. And you can't take it from the table. مش لازم تاخذ من التable, okay? Oh, and here KL, the effective length is 15, and 12 to convert it from feet to inch, and this is R minimum we just calculated from here and here. Right now, this is the cylinderness ratio. Euler buckling stress is this much, which is pi square times 29,000 as a Young's modulus dividing by the cylinderness ratio square, and here is the 24.36 KSI. So here we need to decide if the column elastic or inelastic. So 4.71 under square root 29,000 dividing by F yield or yield stress, which is 50 KSI. This is 113, and still K and the cylinderness ratio is less than this barrier, so we do have inelastic column. So if we do have inelastic column, we're gonna use these formulas. Okay, so here inelastic behavior or column. Let me do it here. Okay, so here F critical is going to be 0.658 to power F yield dividing by Euler buckling stress times yield stress. So we have all this information. So the critical buckling is 21.18 KSI. The nominal strength is going to be the critical stress times the gross area, which we can get it from the, we just calculated, guys, area for the plate and for the wide flange. So هاي اللي هي 1.5 for the plate اللي هي 4 times 3.8 plus on, it's a plus, guys, okay? And plus اللي هي 19.10, the area for the wide flange, you can get it from the manual, okay? So this, the nominal strength is 436.3 kips. So right now let's use the LRFD method. So just times 0.9, you will get 393 kips. And for ASD method is going to be this much here, dividing by 1.67, which is 0.6 times F critical. Okay. Here, just, okay, here, this one, it might be, or it is 436.3 dividing by 1.67, and this is equal to this, guys, because this one, it's equal, okay? It will be this much. Okay, so right now, the answer is, for the LRFD method, this is 393. For ASD method is going to be 262 kips, okay? So this is the compressive strength for this buckling or build-up section. So this is the design strength and this is the allowable strength. Thank you guys for your watching, and please, if you do have any questions, send me a chat on Microsoft Teams or send me an email on my school email. ويعطيكم العافية.